Hey guys, let's have a look at these AC machine nameplates. So, National Electrical Manufacturers Association, NEMA, specified that every nameplate must have this specific list of items, such as the manufacturer's name, rated voltage, full load voltage, frequency, number phases, full load speed, etc. The whole list here shows them.
Here's a clip out of the Canadian Electrical Code 2-100, marking of equipment. All electrical equipment shall bear those of the following markings as listed.
Here we have some samples of nameplates, and these nameplates are going to have all the information that we need to install our motors. Okay, on the left here we have a Siemens nameplate, slightly different than the sample we're going to look at on the right, where we have enclosure types, phase information, and all this stuff, voltage and all these things. We're going to have a look at that. First thing, obviously, manufacturer's name. Who made the motor? Name of the company. Previous slide, that was Siemens. So first thing we look at is the horsepower. Horsepower is the amount of work that the motor can do. This is typically matched to a specific amount of torque that the motor is going to be turning. So we size our motors to the equipment that it's going to power. Okay, so this 1 horsepower motor here, it's going to be sized to a certain amount of foot-pounds of torque that the equipment it's connected to will require for it to operate. We can have a look at that equation here, right? Torque is the twisting turning force produced by the motor. We can calculate that by our horsepower equals the torque times the speed, okay, T times N divided by our constant. Our constant is 5252. So for an example here, let's have a look. If we need a 76.1 foot-pounds of torque at 1725 RPM, we're going to need about a 25 horsepower motor. Now typically you don't size it to just exactly what you need. They're going to size these guys a little bigger, so that might end up being a 30 horse. And then again at 3450 RPM, for the same amount of torque, we're going to need a 50 horsepower. Now we have standard horsepower ratings for all motors. Okay, NEMA established this standard a while ago, North American Manufacturers Association. It has 1, 1.5, then it goes up 2, 3, 5, 7.5, 10, 15, 20, 25, 30, 40, 50, 60, all the way up. Okay, the higher the horsepower, then the larger the increments between sizes. Now you can get higher than 4,000. Okay, you can get up to 20,000 horsepower for some of these motors. Now we have RPM. On this nameplate it says 1720 RPM, and it's pretty obvious this one, that's the revolutions per minute that the motor will be operating at full load. Okay, so when this motor is putting out 1 horsepower of energy onto the mechanical side of its connection, it's going to be running at 1720 RPM. Now the RPMs are different for the different number of poles, as you guys know. The middle column here, synchronous speed, those are fixed depending on the frequency and the number of poles. Okay, so at 60 hertz, our 2-pole is 3600, 4-pole is 1800, 6-pole 1200, and 8-pole is 900. Now the actual speed of the motor, because there's going to be slip, okay, is going to be approximately those values. Those are not solid values. A lot of the 2-pole, 4-pole, 6-pole, and 8-pole motors, they're going to be performing differently. So some 4-pole motors, let's say for example, might have a full load speed of 1775. Some of them are 1725. It all depends on the design and manufacturer of these motors. Next thing we look at is frequency. It's the design frequency in which these motors were intended to operate at. Okay, European and Asian motors quite often run off of 50 hertz. It's getting pretty common to see combination 50, 60 hertz motors. They might have different voltage ratings at that time. Phases. Hopefully this is self-explanatory. Tells us how if it's a single phase or three-phase motor. Okay, two-phase motors do exist where they're 90 degrees out of phase. Extremely rare though in Canada and United States. Type of motor, induction or not. We know the wound rotor motor and the squirrel cage motors are induction motors. Synchronous motors not. So if it's a synchronous motor, it would say type of motor, so it'd say synchronous there. And DC motors, again, slightly different nameplate, but it would say DC motor there. Okay, the next one is the frame. Okay, frame number indicates a type of motor frame. Now by that, why that's important is this frame number here, let's say 143T, that we can take to a table and it's going to give us all the precise dimensions for the motor. The bolt pattern for the feet, the shaft diameter, the difference between where if the motor's sitting flat from the ground to the center of the shaft, the length of the motor and all that. And we're going to have a look at that in a second. So here's the table. Apologize for it being blurry. So if we had, that one was a 143T frame, which is right here. Okay, we have a 143 and a 145T. So we look horizontally here, and we got these letter codes, and we got these dimensions here. Okay, these dimensions coincide with the letter codes on the motors here. So if you notice, let's have a quick look at this guy here. At the shaft here, we have U. Okay, what is U? It's the diameter of that shaft. Okay, right here, that's the U. Okay, so for that 143T motor, we go all the way over to the U column here, and that's 7/8 of an inch. Okay, which is probably approximately 21 millimeters, 20 to 22 millimeters around there. Okay, and then we have, now you have the distance between the feet, right? So if you look at this 2F, same to center motor again, where my little laser pointer is, hope it's working. We have 2F is the distance between the bolt holes where the motors are mounted. We go over, same guy, 143T, and we don't have, oh, there it is there. 2F, 4 inches. Okay, so that's, we know. So when you go to order a motor, you know it's going to fit in the same spot where your old motors was in. Now you got to be careful. There's a couple different letter codes for these. You can see we have the letter codes for U. So a 364T and a 364U, those are different. Okay, that bolt pattern for the 364U down here, it's different than the well, no, that's the same. The end dimension here, that's going to be different. Okay, so just be aware. Some of these the numbers might be the same. These letter codes, they matter also. Okay, and then this is a little detail on the shaft dimensions. So we're looking at, when we look at some of those letter codes that we referenced from the frame code, this is a keyway in this shaft. This is the end of the motor shaft. That shows us the dimensions of all that motor shaft there. Okay, the distance, the width of the key from the opposite side of the shaft to the depth of the key, and then the diameter of the shaft. Here's those letter codes. Okay, I'm not going to read the whole thing. If you guys want to take a screenshot and have a look at it, it's pretty good later. The ones we commonly see is T's and U's. U's are an old code, and T's are what most new motors are. I have a T code on them, or there is no letter code there on a lot of the T frame types. U's are some older motors. You may run into those. Another one I'll point out here is the C letter code. Okay, that means, as I mentioned at the very beginning of AC machines, a pump or some piece of equipment can be mounted directly onto the motor, and the motor can be the actual support for it. That's what the C codes mean. Now we look at voltage. It's pretty straightforward, I hope. That's the maximum voltage we can apply to the motor. Okay, and a lot of these motors are dual voltage, so that means we can have a low and a high voltage setting for them. And some of the lower voltage you see here, it's going to have a little bit of a range, so you can run them at 208 to 230 volts. Okay, and why? What that means is, if we go over here to the current rating, the FLA, full load amps, we have a little bit of a broader current range here. So the windings, the conductors are sized enough to hold that slightly higher current. Okay, so we can put a 208 volts there all the way up to 230 volts. Now the insulation is sized to handle that voltage. Okay, conductor size for current and insulation rating for voltage. And again, here we go, full load amps. Okay, so to match, we have a range of low voltage amps to match the range of lower voltages. So 208 volts. When we run it at 208 volts, our maximum current to the motor is going to be 3.8. When we're running it at 230 volts, the maximum current the motor is going to draw is going to be 3.6. And then 460 volts at the high voltage connection will be 1.8. Now, that's the current the motor is going to draw when it's running at 1720 RPM and putting out 1 horsepower of work. We have the enclosure type. Here we go, a whole list of them. We talked about this at the very beginning. Open drip proof, okay, permits it to be ventilated through the motor windings. Outside external air ventilation can go through. Totally enclosed. It's a totally enclosed motor with a fan on the end. Then we have totally enclosed non-ventilated. Those guys have no external fans. It's just a large football-shaped block of steel, and there's no penetrations going through the enclosure of the motor to the windings and rotor on the inside. It's sealed. Okay, they are typically, again, hose down locations, chemicals, or they might get put in some pretty serious conditions. EXP, you might see TE EXP or TEXP, right? Totally enclosed, explosion proof. Okay, these are for explosion proof areas. Okay, designed to be used in areas that are hazardous environments. Typically, they're all enclosed, non-vented. Duty. Now, this is the frequency in which the motor is going to be operating. This one says continuous, so it can run continuously 24/7. Some of the motors are going to be sized with larger conductors if they have starting and stopping duty, where they start and stop frequently in a short period of time. When we do that to a motor, we're subjecting it to a lot of inrush current in a short time frame. So we have to be able to accommodate that with our conductors. So if it's rated for intermittent duty or sporadic duty, we have to make sure we size our conductors to that. So when we're sizing our conductors, we have to take this duty into account. Max temperature, 40 degrees C. This is the maximum ambient temperature that the motor can operate at before we have to start derating it continuously. Service factor. Okay, I'm not going to read this to you. In a nutshell, it is this motor, technically, this 1 horsepower motor, is actually sized to be 1.15 horsepower. Okay, so it can run effectively up to that amount. Okay, what that does is we're running it slightly unloaded, and it'll run cooler. We're not hitting its maximum limits, design limits. Okay, so also it gives us a little bit of a margin of sizing our overload. So when we have this type of a service factor, we can size our overloads at a little higher percentage than the FLA if we need to. Because we technically can run this motor at, let's say if we're connected it up to 460 volts, we should be able to run this motor continuously at 1.8 amps forever. It should function fully and perfectly at that amount. Okay, if we had no service factor and everything was just sized for that's the maximum current, we eventually could be heating up the windings there. The the load is going to fluctuate. The current is actually, remember, this is RMS current also. Okay, so the peak current is going to be a little higher. So that could over time heat up the windings and prematurely cause failure. Code K, it's a kVA lock rotor code. It's something that the National Electrical Code in the States uses for calculating inrush current. Down here at the bottom, we don't use it in Canada. We simply multiply the FLA by 6 times. Now, the way they calculate it is their FLA is going to be slightly higher than ours. I think we calculate for this guy here, it works out to 100. Sorry, no, that's going to be 10 or 12 amps. In theirs, it would be around 14 amps or something like that. Okay, NEMA design codes. Guess what? Down here at the bottom, rotor design types. Okay, that's on the nameplate too. We have our rotor design type. So if we want to have a specific torque characteristics, we know what type of motor design code we're going to have. So we can have, if it's for a squirrel cage motor, we want it to have a very good starting torque, but we don't care too much about the speed regulation. Okay, we might want to have a D. Okay, it's going to have a higher slip at full speed, but it'll have a really high torque at startup. So we can specify those with this. Okay, efficiency. We all know what this is. Efficiency of the motor. It's the relationship of power in to power out. So the power into the motor is going to be our watts. And if it's a 77% efficient motor, I did the math here for this one. Okay, 77% efficient motor. That means our input power to get that full 1 horsepower of power out is of 746 watts. 1 horsepower is 746 watts. At 0.77 efficiency, we're going to have to push 969 watts of power into that motor. So the difference is our lost energy. Okay, we can also use the nameplate information now with the efficiency to calculate the full load power factor. This power factor is pretty poor, but again, these are just theoretical numbers. So if we can calculate our total kVA at full load, 14.34, and we divide our input watts by our kVA, we're going to get 67%. Pretty poor power factor. Sometimes the power factor is on the nameplate. You may see that. Insulation class. This is the rating in which the insulation in the motor windings can operate at, higher insulation temperature ratings. So this table here shows the temperatures they can get up to and operate at. So if we have a type A motor, it can get up to 105 degrees Celsius. Okay, type B 130 degrees, and all the way up to type H 180 degrees Celsius. So that motor can get really, really hot, work under really hot conditions. Now, in the Canadian Electrical Code, we use table 37 to utilize these codes for conductor insulation and conductor to help size conductors feeding these motors. Here we have model number. Okay, it's a unique number for a specific model of motor. You may see identical model numbers on multiple motors because they're going to have the same characteristics. It's like having the model number for a car. Our serial number is the number signed by the manufacturer, so they can identify a particular motor. They can trace that back to the year it was made, time of day and production run that it was made at. So if there's a problem with the motor, they can trace it right back to its manufacturing. And it's a unique number. Now here we have our connection diagrams. All right, because we have dual voltages on this motor, we're going to have 2 different types of connections. On the left here, we have our low voltage connection. On the right, we have our high voltage connection. Okay, and you guys remember, this is if this is a Y connected motor. I'll tell you a little secret here. If it's a 9 lead delta, typically this middle terminal and the 3, they're swapped. The actual middle terminal on a lot of the delta motors are 3 here and 3 on this side. So it's a little bit of a telltale sign to tell the difference, but technically, if you didn't know that, they could be either 9-lead delta or 9-lead Y. Okay. Now, Canada requires this to be on all the motors too, verified for energy performance. So that's also going to have a minimum efficiency rating tied to it also. Okay, thanks guys. I hope that helps. Talk to you later.